In this video, we'll look at some of the features of functions, especially the features of the graphs of those functions. And one of the key features we're going to spend a lot of time on is the average rate of change. Now, if we have a function like f of x equals x squared minus x minus 2, then that function will have a corresponding graph. That graph will have features that we can use to describe it. So here we have this function, f of x equals x squared minus x minus 2, and its graph. What sort of features could we use to describe this graph to another person? One of the first features we could use is what points these things go through, that the graph goes through. We could also talk about the movement of the graph. We could also talk about like the lowest point on the graph. And those are the types of things we're going to talk about. Let's start out with points on the graph. So one way to talk about a graph is to give a bunch of points that are on that graph. We did this in a previous video. We have our y value is the output f of x. And so whenever I plug in a certain value for x, I will get a corresponding value of y, which means that my function or the graph of my function goes through the point x comma y. So whenever we plug in x, we get out a y value. Now, a couple of points of high interest to us are the x-intercepts and the y-intercepts. So those are some key points, x-intercepts and the y-intercept. An x-intercept is a point which is on the graph of the function and also on the x-axis. That's why it's called the x-intercept. Since all points on the x-axis have form x value comma 0, any x-intercept is going to have x value comma 0. So in other words, for an x-intercept, the y value is always 0. A function can have no x-intercepts. It is possible for a function never to cross the x-axis. It's also possible for a function to cross the x-axis once. And obviously we can, well, not obviously, but it's also true that a function can cross the x-axis multiple times. So a function can have any number of x-intercepts. It can have 0 x-intercepts, 1, 2, 3, 4. In fact, some functions can have infinitely many x-intercepts. The other type of intercept is the y-intercept. That's a point that's on the graph of the function and the y-axis. The y-axis has points that are always of the form 0 comma y. Therefore, every y-intercept is going to have the form 0 comma y. In other words, a y-intercept has 0 as the x value. Now, because the y-intercept is a vertical line, or excuse me, because the y-axis is a vertical line, a function can only have at most one y-intercept. If it has two, then it's not a function because it fails the vertical line test. So a function can only have one y-intercept, or it could have 0 y-intercepts. It could have 1 or 0. Those are our only options for y-intercepts. Let's take a look at this example. And let's list a few points that the function goes through. We can do this by looking at the graph. We can also do this by plugging in values into my function f of x. I'll do it both ways. I'll do it algebraically first, where I plug in some x values, and then I'll do this by looking at the graph. In this case, it didn't specify what values of x to plug in, so it doesn't really matter what values of x I plug in. Let's say I plug in, excuse me, the number 1. I would get 1 squared minus 1 minus 2, which is a -2. Therefore, I know my function goes through the point 1 comma -2. You can do that for any other values as well. Let's say I wanted to plug in the number 0 into the function. I would get 0 squared minus 0 minus 2. Notice that's also a -2. So in terms of another point on the function, on the graph of the function, another point would be the point 0 comma -2. You can plug in anything you want, technically. Let's say I plug in 3 into the function. Well, then I would get 3 squared minus 3 minus 2. That's 9 minus 3 minus 2, which is 4. So we know that the graph goes through the point 3, 4 as well. And you could imagine any x value you wanted, we could plug in. So that's how we did that in a previous video, by looking at plugging in x values into the function, getting out y values, getting out the corresponding y values. Now, we could have also done that visually. So for instance, plugging in 1 into the function, if I look at just the graph itself, when I plug in 1, we would go down to where the graph is. It looks like it's crossing through the point 1, -2. If I plugged in 0 as my x value, it looks like it's going through the point 0, -2. So let's write those types of things down. So just visually, we can see that 0, -2 is one of the points. We already found that one. We can also see that 1, -2 is another point. It looks like this is 0.5. This lowest point here looks like to be 0.5 and then -2.25. If you want to check that, you can always plug in 0.5 and see that it does, in fact, give you a -2.25. Other points, well, notice that the point 2, 0 is on the graph. Also, the point -1, 0, which is over here, is on the graph. And then you could look at lots and lots of other. It looks like 2.5 and then 1.75 is on the graph. That's another one, 2.5, comma 1.75. You can again check that. And so on and so forth. You can do lots and lots and lots of these examples. You could do 1.5 and then negative 1.25, it looks like. Obviously, my picture only goes up to 3. So the 0.34 is somewhere up here. It's not on this picture. If I did this graph using technology, I could zoom in and zoom out and see some other points as well. But that's the main idea. Now, notice that this graph had two x-intercepts because they crossed the x-axis at two different places. So the x-intercepts for this graph, we already found them. They are the negative 1, comma 0 and the 2, comma 0. So those 2 points are our x-intercepts. We have 2 of them because the graph crossed the x-axis twice. We have one y-intercept, and that's at 0, negative 2. So the y-intercept there's only one of them, and it is 0, negative 2. So there you go. There's a bunch of points on the graph. A couple of those happen to be x-intercepts. One of those is the y-intercept. And again, you can only have one y-intercept at most because if you have two y-intercepts, then we're no longer dealing with a function. That would fail the vertical line test. But there you go. The other way I said when I was describing the graph of talking about the function is the idea of movement. And the basic idea of movement consists of increasing or decreasing. Is our function increasing or decreasing? It could be constant as well. We'll mention constant in a moment. A function is increasing on an interval if for every two x values on that interval, where the x value of A is less than the x value of B, we have that the output of the function when I plug in A is less than the output of the function when I plug in B. Now, that's just a fancy way of saying as x gets bigger, y also is getting bigger. So as the x values are growing, then the y values are also growing. That's what increasing means. A function is decreasing on an interval if for every two x values on that interval, where a is less than b, we have the output f of a is greater than the output f of b. Again, that's just a fancy way of saying as x grows, y is getting smaller. There's also something called being constant. A function is constant if the outputs are always the same on that interval. So this is describing movement. And when you think about x getting bigger, that's moving left to right. So think about how you read a book in English, obviously. When we read, our eyes go left to right. And increasing means if I look at that graph as it's moving left to right, are the y values getting bigger? Decreasing means as I move left to right, are the y values getting smaller? And then constant means the y values are staying the same. If the y values stay the same, then we get a horizontal section. Now, if we're just given an interval, obviously we can have our function be increasing on the entire interval, or decreasing on the entire interval, or constant on the entire interval. But sometimes on a specific interval, we'll have some decreasing and some increasing. So on certain intervals that we pick, on certain graphs, there's going to be combinations of increasing and decreasing or constant. Let's take a look at the graph that we've been viewing. F of x equals x squared minus x minus 2. That gives this graph. And we're going to say, what's the function doing? Well, as I move left to right means I'm increasing in x values. Then this graph is moving down for a while until we get to this bottom point. And then once we hit that bottom point, then we start moving back up. So it's decreasing, and then it hits a bottom point, and then it's increasing. And we can say what that function is doing on specific intervals, whether it's increasing, decreasing, it's neither increasing nor decreasing strictly, or it's doing both, or it's constant. This graph doesn't have any constant portions where it's just horizontal, but other graphs could. So let's take a look at this. So when we say on the interval from -2 to -1, we're saying the x value of -2 to the x value of -1. So basically, in this section where I go from x value of -2 to x value of -1, as you look at that, obviously each point is moving down as I move left to right. So what I would say is on that interval from -2 to -1, the function is decreasing. Now from -1 to a positive 1.5, from -1 to a positive 1.5, so 1.5 would be about here. Obviously, my function goes down for a while, hits that bottom point, and then turns back up. Usually what we say is that in this case, the function is neither strictly increasing nor strictly decreasing. So it's doing neither. All right. Maybe neither is the key there. It's actually kind of doing both, but when I say strictly just means only increasing. Strictly decreasing means only decreasing. So it's kind of doing a combination of both. We're going down and then up. And so it's not just increasing, it's not just decreasing, because it does both. Again, strictly is the language we use there for it only does that. So neither strictly increasing nor strictly decreasing. Now the next section, or excuse me, that we're asked to look at is from 1 to 2, and then from 0.5 to 2.5. Let's take a look at the section from x value of 1 to x value of 2. That's this section here. And notice that as a point moves along that graph, if it moves left to right, then we're always going up. So from 1 to 2, the function is increasing. From 0.5 to 2.5, well, 0.5 is right here. 2.5 actually is a little bit off the charts, but that's okay. 2.5 right there. Well, from 0.5, 0.5 looks to be where the lowest point is. And then I move up. It's always increasing in that section as well. So in that section, we're also increasing. So from -2 to -1, the function's decreasing. From 1 to 2, the function is increasing. From 0.5 to 2.5, the function's increasing. From -1 to 1, or -1 to 1.5, I said, the function's doing neither strictly decreasing nor strictly increasing. Let's look at another example. Here's the graph of a function. Now, in this function, we're not provided the actual function expression like we were in example 2, but we can still see the graph of the function, and based on what we know, we can say whether on these intervals the function is decreasing, increasing, or neither strictly increasing nor decreasing. If you want to try this on your own, push pause on the video and try it on your own. I will write it down in a couple of seconds. All right, so let's do this. Hopefully you got a chance to try that if you wanted to. So from -3 to -2, -3 to -2, that's x values, -3 to -2. Our function is going up. So on that interval from -3 to -2, the function is increasing. From 0 to 2, let me write that down as well. From x equals 0, this point, to x equals 2, this point, our function is always going down. Now it's going down at slightly different rates as I move along here, but it's still going down everywhere. So the function is decreasing in that section. From 0 to 4, well, from 0 to 4, we're going to have pieces where it goes down and then pieces where it goes up. By the way, notice that at this point, we're at 0, -1, and at this point, we'd be at 4, -1. Hopefully, you can see that. So we actually started and stopped at the exact same y value. that does not mean our function was constant. In fact, our function is not constant. It goes down some and then back up some. So just because it started and stopped at the same y value doesn't mean the function is constant. So we went down a little bit, up a little bit. But what we would say is that the function is neither strictly increasing or decreasing. I'll just say for shorthand, function is neither. It's not strictly increasing. It's not strictly decreasing. What about from 3 to 5? Well, from 3 to 5, x value of 3 to x value of 5, the function in that section is going up. And so we would say that the function is increasing in that section. By the way, notice that in the 3 to 5 section, the function is increasing. Also in the -3 to -2 section, the function is increasing from -2 to -1. Maybe not -1, but from -2 to -1.5, the function is increasing. But just because two things are increasing doesn't mean it's increasing at the same rate and in the same way, obviously. So this is a slower increase. This is a faster increase. I just wanted to point that out because that's something we're going to look at later. So this is how we determine whether a function is increasing or decreasing on a given interval. Another question that could be asked is, we could ask to determine the intervals where the function is increasing, where the function is decreasing, and where the function is constant. Now, this graph doesn't provide any horizontal sections where the entire graph is just flat horizontal. So this one, we're only going to have decreasing and increasing, but we can see we decrease until we hit this point, and then we move up until we hit this point, and then we move back down. I've labeled those points because they're really hard to spot just using the visual. One of them has x value about -1.58, and the other has x value about -0.42. All right, so in this function, it looks like that this pattern goes on forever to the left. So it looks like as you move to the left, the function goes up to infinity. And as you move to the right, you go off and this pattern goes forever. So basically from x value from -infinity all the way up until we hit this bottom x value of -1.57735, the function appears to be decreasing. Now we're going to utilize the interval notation we've dealt with before. So with interval notation, we can say from -infinity up to -1.57735, our function is decreasing. Once we hit that -1.57735, then our function turns back up, and now the y values are increasing after I've hit the -1.57775. 735. And they increase up until I hit this point of negative 0.42 roughly. So on the interval from roughly negative 1.57735 up to negative 0.42265, the function is increasing. I'm using open brackets because at that specific point of negative 1.57735, if you move one way, if I'm moving one way into it, I'm decreasing into it, and then I'm increasing out of it. So I don't want to say it's strictly decreasing or strictly increasing at that specific point because we change directions at that specific point. Now, once we hit negative roughly 0.42, then our function turns down again, and once again, we're decreasing. So in interval notation, from that negative 0.42 number up to positive infinity, our function is decreasing. And that's how we would write the intervals where our function is decreasing and our function is increasing. From negative infinity down to the negative 1.58, we're decreasing. From negative 1.58 to negative 0.42, we're increasing. And then from negative 0.42 up to positive infinity, our function is decreasing. So that's how we could lay out intervals where our function is increasing and where it's decreasing. Now in this example, we had this point and this point where we changed from decreasing to increasing, and the other point where we changed from increasing to decreasing. Notice that when we went from decreasing to increasing, that point wound up at sort of the bottom of a valley. Where we changed from increasing to decreasing, that point ended up at what we call the top of a hill. Those points are the idea of what we call extrema. So a function has a local, so we'll start with local extrema. A function has a local maximum at x equals b if there's an open interval containing b such that the y value or the output value you get out when you plug in b into f is greater than all other output values when you plug in anything else into f that's within that open interval. In other words, if we're at a spot which has the highest y value around it, then it's a local maximum. A similar thing can happen with a local minimum. A function has local minimum at x equals b if there's an open interval containing b such that the y value is smaller than the other y values around that point. So a local maximum point is a point which is the highest point in a local region around itself. A local maximum value is the y value of that point. A local minimum point is a point with the lowest y value around in a region around itself. And the local minimum value is that lowest y value. Now, this is local extrema. So basically, what's going to happen if we see a maximum, it's going to be the highest point around in a region surrounded by that point. Local minimum point is going to have the lowest y value in a region around that minimum point. That's the idea of local extrema. A local maximum is a point where the y value is larger than other y values around it. So that's what we mean by open interval containing the point. We have to go a little bit left of the point, a little bit right of the point. And if it has the largest y value in that region, then that's the maximum. A local minimum point is where the y value is smaller than all the other y values around it. Again, we're talking about in an open interval. So you go a little bit to the left of the point, a little bit to the right of the point, and say in this little region, does that point have the highest y value? Now, the other idea of extrema is an absolute extrema. Extrema just means it could be the smallest or it could be the maximum or minimum. So absolute extrema means an absolute maximum or an absolute minimum. And that means it has essentially the biggest y value. If it's an absolute maximum, it has the biggest y value for all points in the domain. An absolute minimum of a function is going to have the smallest y value for all points in the domain. Sometimes the absolute maximum and the absolute minimum are called universal maximum and universal minimum in other books. So you may see that as well. You may see the term universal maximum, universal minimum. The more common term is absolute max and absolute min, but there are other terms as well. So let's take a look at the original graph that we had and find local and absolute extrema for this function. So local minimums and maximums, absolute minimums and maximums for this function. In this example, we have to kind of look closely, but we've already found some points using our function expression. You'll notice that if I look at this point here, which is at sort of the bottom of a valley, this is 0.5 comma negative 2.25. This is the only point that's smallest of all the points around it. So in other words, if I drew a little section and I focused on this point here is smaller than all of the other points around it. On the other case, if I took a different point, let's say I took the point 2.5, 1.75. So I took this point. If I drew a little bit to the left and a little bit to the right, there'd be points that are bigger than this one. There'd be points that are smaller than this one. So it looks like this is the only point which is bigger than or smaller than all of the other points in an open region around it. And that's clearly a local minimum. Like I said, we've already calculated what this is. Earlier, it is 0.5 comma negative 2.25. Or if I didn't calculate it, I at least said it was that. There are no local maximums. There's no peak values. So for local maximum, we'd either write none or we'd write does not exist or DNE for does not exist. So no local maximums exist. Now, how about the absolute minimum? That means the smallest point amongst all other points in the entire graph. And once again, the smallest point in the entire graph is that local minimum. And therefore, the absolute minimum point is also 0.5 comma negative 2.25. There's no maximum because this graph shoots off to infinity on both sides. So since we can get as big of numbers as we want, we say that there is none for our absolute maximum, or another way to say that is our maximum does not exist. By the way, I'm writing the absolute minimum point and the local minimum point. Some people would just ask for the minimum value of the graph, and the minimum value is just the minimum y value, negative 2.25. And that would be both the local minimum value and the absolute minimum value. So the local minimum point, the absolute minimum point, there's only one of them in this graph. That's 0.5 comma negative 2.25, has minimum value of negative 2.25. And there's no local maximum and no local maximum and no absolute maximum for this graph. Let's take a look at this example. This is the graph we've dealt with before, where we found the sections where we were decreasing and increasing. And let's find the local and absolute minimum values, maximum values, minimum points, maximum points for this graph. If you want to try this on your own, push pause on the video and then try it on your own. In a couple of seconds, I will write down the answers. Now, in this case, it's pretty easy to see that the point where we switch from decreasing to increasing is going to be a local minimum, because if I draw an open interval around that point, that is going to have y value that's smaller than everything else. If I draw an open interval around this point where we switch from increasing to decreasing, then that's going to have a y value that's bigger than everything else. So this gives us the fact that this graph has one local minimum and one local maximum. All other points on this graph, no matter where I draw them, If I put a little bit, go a little bit to the left and go a little bit to the right, I'm going to find points that are bigger than and less than that point. So no matter where we're at, if you go a little bit to the left, a little bit to the right, we find points that are bigger than or smaller than that one. So we can see that the local minimum happens at the point roughly negative 1.58 and comma negative 0.38. And that means the minimum value is that negative 0.38 roughly. When I'm talking about these, I'm obviously rounding to a couple of decimal places just to make it not as cumbersome. So that's the local minimum, this point right here, at about negative 1.58, comma, negative 0.38. The local maximum point is at that negative 0.42, comma, 0.38. And that means that the local maximum value is the y value of about 0.38. So this graph has one local minimum, one local maximum. However, if you look at the left-hand side, as you move left, this graph is shooting off to infinity. So while this point that we just saw was a local maximum, it is not the absolute maximum because we have this other side which is higher. The same thing with local minimum. This local minimum is not the absolute minimum because the absolute minimum doesn't exist because the graph goes down to negative infinity. So the absolute minimum point does not exist for this graph. And in the same way, we do not have an absolute maximum point. So the absolute maximum point does not exist either. Same thing with the minimum value, the maximum value, those do not exist. So in this case, we have a local minimum, a single local minimum, a single local maximum, and then no absolute minimum, no absolute maximum. Again, just for the record, absolute minimums and maximums can also be called universal minimums and universal maximums in other books. Let's do one where we're not given the actual graph, but let's put all of these features that we've learned so far together. Let's take g of x equal to x to the fourth minus x to the third minus x squared plus x plus 4. And let's find a few points on that graph, determine the intervals where it's increasing and where it's decreasing, find any local maximum and minimum values, maximum and minimum points, find any absolute maximum and minimum points, maximum and minimum values. For this, we're going to be using technology to make our lives a little bit easier. So you can either graph using a function, a computer and using Desmos, or you can use your calculator like using the TI-84. If you don't know how to graph using the TI-84, then obviously there will be a companion video to show you how to do this using the TI-84. However, because of simplicity's sake, I am going to do this using Desmos in this example. As always, if you want to try this on your own, go ahead and try it on your own. And then see if we got the same answers. When I graphed this, I ended up with a graph of the function that looks like this. Now, obviously, I could use this function expression to plug in numbers, and that could give me points. But I can also just kind of trace around this graph using my cursor, and it'll follow and see some of the points on this graph. You can also use the trace feature on your TI-84 calculator to do the same thing. So for instance, if I want to find some points, obviously -1, 4 is a point on the graph. If I were to plug in 0, I'd get 0, 4 as a point in the graph. If I plugged in a +1, I'd get +1, 4 as another point on the graph. Now, you can zoom out on Desmos pretty easily, and you can see that, for instance, 210 is another point on the graph. If I zoom out even further, you'll be able to see that -2, 22 is another point on the graph. And you can do this pattern as far as you want. So for instance, it looks like, where's 3 at? 3 will be pretty close. Oh, there it was. 352 looks to be a point on the graph. So that's a lot of points on this graph. That's not the only ones you could find, okay? There's some that Desmos highlight and some that your TI-84 calculator can figure out. I do want to point out that 0, 4 is the y-intercept. 0, 4 is where this graph hits the y-axis. And you'll notice that this graph never crosses the x-axis. So this graph doesn't have any x-intercepts. Let me write those things down before we move on. So we were supposed to find a few points. We said -2, 22 was one of the points that we looked at. And another point was the point -1, 4. Another point was 0, 4. Another point was 1, 4. Another point was 2, 10 that we saw. And another point was 3, 52 that we saw. And again, we can check those if we want by just plugging in the corresponding value for x into g and see that that gives us out the right y value as our output. But those are some of the points we saw. Now, again, there's lots and lots of other points. Now let's take a look. Oh, I'm sorry. Before I do that, I do want to mention that we do have one y-intercept, and that's what I already mentioned, 0, 4. There are no x-intercepts. All right, so those are the points that I'm looking at. Obviously, we could have other points. We don't have to list all of these points, but those are some interesting ones. Now let's take a look at the intervals where this function is decreasing and increasing. So it looks like from negative infinity down to this bottom point here, the function is decreasing. And then it starts increasing again till it hits this point right here. So from this point, whose x value is negative 0.64, to this point, whose x value is 0.39, we're increasing. And then from 0.39 down to 1, or up to 1, excuse me. So from x value of 0.39 to x value of 1, the function's decreasing again. And then from x value of 1 and beyond, then we're increasing again. Now, Desmos is nice in that if you hold your cursor over the point, it will give it to you. And the bottom of valleys are usually highlighted. The tops of hills are usually highlighted. So usually you can just click on those and it'll give you the point. If you're on using your TI-84, then you can just find the minimum values using the TI-84s, find the maximum values using the TI-84s. Find the minimum and maximum points. But there you go. So decreasing in this section, increasing in this next section, decreasing again, and then increasing again. Let's go ahead and write that down on the Word document. So on our graph, on the interval from negative infinity up to negative 0.64-ish, I'll round it to 2 decimal places this time, the function is decreasing. On the interval from negative 0.64 up to the x value of 0.39, the function is increasing. From 0.39 up to 1, the function was decreasing again. And on the interval from 1 to infinity, the function is increasing. So those are the intervals where our function is decreasing and increasing. From negative infinity up to about that negative 0.64, the function was decreasing. From negative 0.64 to positive 0.39, our function was increasing. from positive 0.39 to 1, the function was decreasing, and then from 1 and on, the function is increasing. So there we go. Decrease, increase, decrease, increase again. All right. The other thing we want to do is find the local minimums. Notice that there are two places where the points are at the bottom of valleys, or the bottoms of valleys. That is this point where the x value is about negative 0.64, and this other point, which is x value of 1. So those are two local minimums. If you drew a little open section around those 2 points, they would be the smallest, they would have the smallest y values of points in that little region. And on the other hand, this point up here at top has the largest y value in the region. So if I highlight that point, which has x value of 0.39 roughly, then that has the largest x value in the region, or not x value, y value in that region. So we have two local minimums and one local maximum. Let's write that down. So for this function, local minimum points, we said we had two. I'll round things to a couple of decimal places. Negative 0.64, comma, 3.38 was that first minimum point, local minimum point. The other local minimum point was the 0.14. By the way, if it asks for the local minimum values, it would be the 3.38 and the 4. We had one local maximum point, and that was the point, again, rounding to two decimal places, that was 0.39, comma, 4.20. And again, the local maximum value would have been 4.20. So these are the local minimums and the local maximums. Now, what about the absolute minimum and the absolute maximum? Since we have two local minimums, they can't both be absolute minimums. You can see that the smallest point in the entire graph, or the smallest y value on the entire graph, is at this point here of negative 0.64, comma 3.38. That's obviously lower than 1, comma 4. And it's lower than every other point as well. So the absolute minimum point is just that one, negative 0.64, comma 3.38. Now the absolute maximum point does not exist. We have a local maximum here, but you can see as we move to the right, as we move to the left, my graph goes up to positive infinity. And if it shoots off to positive infinity, then there is no maximum point. So there's no absolute maximum. The universal maximum does not exist. You could say that as well. The absolute minimum does exist. The universal minimum doesn't exist. It's at this point of negative 0.64, comma 3.38. Let me write that down as well. As stated, the absolute minimum point is negative 0.64, comma 3.38. The absolute maximum point, we're either going to say the absolute maximum point, there is none, or we're going to say the absolute maximum point does not exist. So 2 ways of saying that. There you go. So we have, in this case, 2 local minimums, 1 local maximum, 1 absolute minimum, and no absolute maximum points and values. We saw where we were decreasing and increasing. We saw some points on the graph. In particular, we saw the x-intercepts, that there were no x-intercepts. And we saw that there was 1 y-intercept for this graph. Again, we use Desmos. You can also use your TI-84. I'll try to show that in a companion video. The last concept that we're going to look at in this section is the concept of the average rate of change. That is how fast a function is changing from one point to another. And when we say how fast a function is changing, we have to say on average how fast its function is changing. All right. So in other words, if I drive 10 miles, for part of the time, I may be driving at 30 miles per hour. And for part of the time, I may be driving at 40 miles per hour. And we look at sort of the average speed over that 10 miles as our average rate of change. So when we think of average rate of change, we're really thinking about the change in the y values on average. So when we talk about change in y values on average, we're talking about how much difference there is in 2 y values divided by how long of a span in the x values did we travel. If I have 2 points, point 1 we'll call x1 comma y1, and point 2 we'll call x2 y2, then the average rate of change is just going to be a fraction where I take the y value of point 2 minus the y value of point 1 in the numerator, and then divide by a denominator of x value of point 2 minus x value of point 1. This formula, y2 minus y1, all divided by x2 minus x1, should look familiar because it is the slope of a line between 2 points. So the average rate of change is essentially finding the slope of a line between 2 points. And those 2 points are coming from my function. Let's do the example in front of us, which deals with the function we were just dealing with, g of x equals x to the 4th minus x to the 3rd minus x squared plus x plus 4. And we're going to find the average rate of change from x equals 0 to x equals 2. And then we're going to find the average rate of change from x equals negative 2 to x equals negative 1. And then we're going to find the average rate of change from x equals negative 1 to x equals 1. Oftentimes, what we'll do is we will rewrite average rate of change, or we will use shorthand average rate of change as just ARC. In order to compute this, we obviously need to know the y value of 0.2, the y value of 0.1, the x value of 0.2, and the x value of 0.1. In these cases, I'm just given x values. So I need to find the corresponding y value. Let's plug in 0 into my function g. If I plug in 0, then I'll just get out a 4. So that means that my graph goes through the point 0, 4. In fact, we already knew that because of earlier work with that function in the last example. Also, if we plug in 2, we should get a 10. Again, we also saw earlier that this function goes through the point 2, 10. So the average rate of change for this function from x equals 0 to x equals 2, I'll call 210 the second point and 0, 4 the first point. So the y value of the second point is 10 minus the y value of the first point, which is 4. The x value of the second point, which is 2, minus the x value of the first point, which is 0. I end up with 6 over 2, which is a 3. So the average rate of change between these two values is 3. Again, I'm using, you could either algebraically plug these in to get these points, or you can remember that we just found a bunch of points, right? 0, 4, and then 2, 10 were 2 points. And then I'm finding the slope of the line between those 2 points. Let's do the calculations for this next one. Again, the first thing I'm going to do is find the points I'm using. If I plug in a -2, I get a 22. So we were at the point -2, 22. That was one we found before as well. If I take and plug in -1 into my function g, turns out I get a 4. Again, that was one of the ones we found before as well. So the average rate of change here, I will call -1, 4 the second point, and -2, 22 the first point. So I take the y value of my second point minus the y value of my first point, that's 4 minus 22, divided by the x value of my second point minus the x value of my first point, which is -1 minus -2. I'm going to get the fraction -18 divided by a +1. So the average rate of change is -18. By the way, oftentimes average rates of change do not come out to be integer values, but in a lot of my examples here, they will. But a lot of times they won't come out to be nice whole number or integer values. Let's do one more example before I show what's going on the graph. If you plug in -1 into my g function, you get a 4. So we know We're at the point -1, 4. If I plug in a +1 into g function, I also get a 4. And again, we saw that point as well earlier. We're at 0.14. So the average rate of change is, on average, how much do the y values change? Well, the y value of the second point is 4. The y value of the first point is 4. The x value of the second point is 1. The x value of the first point is -1. So we get an average rate of change of 0 in that case. Now, what average rate of change is doing is it's telling you on average, how is your function changing? Not just if it's increasing or decreasing, but how fast it's increasing or decreasing over that range. So that is a really nice feature to know. How fast is the function changing between 0 and 2 on average? And it says it's 3. Visually, what this looks like, again, I've highlighted the points that we're dealing with in the first average rate of change. That's 0, 4, and 2, 10. What we're saying is, how is this function changing on average? For a little bit, it goes up, and then it goes down, and then it goes up really steeply. If I average that out, that means I would have taken basically just a straight line from 0, 4 to 2, 10. I would have said, what is the slope of that line? That would have been the average rate of change. And the slope of that line, well, since we go up 3 over 1, then up 3 over 1 again, the slope of that line is 3. In fact, that line is y equals 3x plus 4 in this case. So average rate of change is connecting those 2 points and saying, what is the change between this one and this one on average? Again, it doesn't mean on a whole, because sometimes we're going up, sometimes we're going down, but on average, the change is going to be the slope of that line. So that's what we ended up with. And so let's check the other one out. So if we went from -2, 22, that's way up here on the graph, down to, or up to, depending on whether you're using up or down, -1, 4, we're going from this point to this point. Notice that that's going to be a really steep decline. And that is going to be connected. If you connect those 2 points, on average, the change is going to be -18. So the slope there is -18. If I look at going from -1, 4 to +1, 4, obviously we decrease and increase and decrease again, but essentially, on average, there was no change. Yes, we decreased some, but that was offset by the increases. And this increase was offset by this decrease. And so on average, we stayed the same and we got slope 0. Now you can do that with any 2 points. Any 2 points on here, you can basically find the slope of the line that connects those 2 points. So this one, which has x value of negative 1.2, and this one, which has x value of positive 1.2, connect those, get the slope. Obviously, as you move around, those slopes will change all the time. And you're saying, on average, how are those things changing? So there you go. That's the idea of average rate of change. It's the slope between 2 points on a graph. And in general, it tells you on average how fast is that graph changing between those 2 points. Let's do another example with a function that we haven't looked at yet. Let's take the function h of x equals negative x squared plus 5x plus 2, and let's find the average rate of change on the interval from 0 to 4, the average rate of change on the interval from negative 2 to 3, the average rate of change on the interval from 2 to 6. On the interval from 0 to 4 means x value from 0 to x value of 4. And similarly with these other two. If you want to try this on your own, push pause on the video and do it on your own. In a couple of seconds, I will calculate those average rates of change. All right, so first thing we need to do is establish the points that we are at. So if we're going from x value of 0 to x value of 4, I start at the point which has x value of 0, and I end at the point which has x value of 4. So I'll say h of 0 and then calculate that. That's negative 0 squared. Notice that the negative is on the outside of the parentheses, plus 5 times 0 plus 2, which when we calculate that gives me a 2. So I know that the first point, which I'll call point 1, is the point 0, 2. The second point I get by plugging in 4. That's negative and then parentheses 4 in my parentheses and square it, plus 5 times 4 plus 2. When I do that calculation, that is negative 16 plus 20 plus 2, which gives me a 6. So my second point is the point 4, 6. Now I'm ready to find the average rate of change. The average rate of change is the difference in y values. That's going to be a 6 minus 2 divided by the difference in the x values, which is a 4 minus 0. In this case, that's going to be 4 over 4, which means that the average rate of change on that interval was 1. The average rate of change of this function on that interval was 1. In the second example, the average rate of change for this function, we're going to be using a negative 2 as my first input. I have to do negative of negative 2 squared plus 5 times negative 2 plus 2. Be careful, especially with all those negatives flying around. The first piece gives you a negative 4. That's minus 10, and then plus 2. So that's going to be a negative 12 as my output. That means we're at the point -2, -12. I do a similar thing with 3. When I plug in 3, -3 squared plus 5 times 3 plus 2. That's going to be -9 plus 15 plus 2, which is an 8. That means the point that my graph goes through is 3, 8. Now I'm ready to find the average rate of change. The average rate of change for this function on that interval can be calculated by taking 8 minus -12 divided by 3 minus -2. That's 20 over 5, which is 4. So while both sections on average, we are increasing, we're increasing at a much faster rate over the section from -2 to 3 than we are from 0 to 4, again, on average. Let's do this last one. Plug in a 2 into the function h. That becomes -2 squared plus 5 times 2 plus 2. When I calculate that, that's -4 plus 10 plus 2, which is a +8. We know we go through the point 28. And then plugging in 6 into h, -6 squared plus 5 times 6 plus 2. That's going to be a -36 plus 30 plus 2, which gives me a -4. So we're at the point 6, -4. Now I'm ready to do the average rate of change. Average rate of change is equal to always change in y values -4 minus 8 divided by change in x values 6 minus 2. That's a -12 over 4, which is a -3. So we can say on this interval from 2 to 6, on average, the function is decreasing since we have a negative average rate of change. So positive average rates of change means our functions are increasing. Average rate of change, which is positive, functions increasing. Again, faster increasing corresponds to faster average rates of change. And if we have a negative average rate of change, that means our function is decreasing. And if it's a, quote, bigger negative number, meaning larger in absolute value, then it's increasing or decreasing really quickly. Just to look at a visual of this graph, h of x is this graph. You can do this with your TI-84 as well if you don't want to use Desmos, or if you can't use Desmos. Our 2 points that we started out with are 0, 2 and 4, 6. And if you draw the line between them, that line is going to have slope 1, we found out. So the average rate of change between these 2 points is 1. Our Next 2 points were -2, -12, and 3, 8. We'd have to go down to -12 there. So from here to here, and then the slope of that line we found to be 4. Okay. And then the next 2 points were 2, 8 and 6, -4. And obviously we were decreasing on average going from 2, 8 to 6, -4. So that's why we got a -3. So decreasing on average corresponds to negative average rates of change. Increasing on average corresponds to positive average rates of change. And then you can do any 2 points you want and play around with that as you like. So move points over and figure out the average rate of change. Any 2 points that we like. Obviously, if we're in an increasing section, then the slope is going to be positive. If we're in a decreasing section, then the slope is going to be negative for reasons we talked about earlier. Obviously, on this graph, the average rates of change vary because the slope between these 2 points vary as we move the points around. So depending on which 2 points we pick, we'll get different average rates of change. And we saw that in our example. Let's do one more example to find the average rates of change. And let's use the following function. F of x equals 1/2 x minus 6. You could have also said 0.5 x minus 6. We'll find the average rate of change on the interval from 1 to 5, the average rate of change on the interval from -2 to 3, and the average rate of change on the interval from 5 to 8. If you want to do this on your own, push pause on the video. I'm going to do this fairly quickly. Hopefully it's not too much. But when we plug in an x value of 1, we get a y value of -5.5. When I plug in the x value of 5 into the function, you can calculate this. I'm not going to spend too much time. You get a -3.5. So if you calculate the average rate of change, the difference in y values is going to be -3.5 minus a -5.5. And that's going to be divided by 5 minus 1, the change in the x values. I know I didn't write the points out, but we can infer what those points are. X value of 1 has a y value of -5.5. X value of 5 has a y value of -3.5. When we do this, we end up with 2 over 4, which is also 1/2. Let's move on to the next one. When I plug in a -2 into my function f, I end up getting an output of -7. Again, you can calculate that on your own, or you can just trust me, or you can graph the function. When we plug in an x value of 3 into the function, we end up with a negative 4.5 as the corresponding y value. So the average rate of change, which I just am writing ARC in shorthand, becomes negative 4.5 minus negative 7 divided by 3 minus negative 2, change in y values divided by change in x values. When you do the calculations, you get 2.5 divided by 5, which is also 1/2. You probably can anticipate what's going to happen in this last calculation. I'm going to do the calculation anyways, though. When we plug in 5, you get a negative 3.5. We saw that earlier. When you plug in 8 into the function, you get a negative 2. The average rate of change becomes negative 2 minus minus negative 3.5. Divided by 8 minus 5. That becomes 1.5 over 3, which again is 1/2. Notice on each of these intervals, the average rate of change was 1/2. Now that's because of what this function is. This function is giving me the graph of a line. So we call it a linear function. Therefore, since this was the graph of the line, it's going to have constant rate of change. In other words, the slope of that line is going to be constant in between any 2 points. And obviously the slope of that line is 1/2. We can graph this if we want. We had a straight line as the graph of our function. And so if I chose any 2 points, let's pick the last example we did, the one where x went from 5 to 8. So we're talking about that. Well, what's the slope of the line that connects those 2 points? Well, the slope of the line that connects those 2 points is the line itself, or it's the slope of the line we're using, which is 1/2, right? The line we're using has slope 1/2, so therefore the average rate of change. And it doesn't matter which 2 points we pick. We can move these around in any way. And if I draw a line that connects these 2 values, connects these 2 points, well, it's going to be the line itself. And so rate of change is the slope of that line. And if we write the line that connects them, then that's what it looks like. So lines have constant rate of change of whatever the slope is. Okay. Other graphs we saw do not have constant rates of change, and the average rates of change can vary depending on where we put our points, but not on lines. Lines always have average rate of change of whatever the slope of the line is. So that's the idea of the average rate of change. Average rate of change is giving me how fast my function is changing, how fast we're increasing or how fast we're decreasing, depending on whether the average rate of change is positive or negative. And That is obviously on average. So what is the average speed? It may vary as we go through, but it's basically telling you something about the speed of increase or the speed of decrease. So that is a very nice feature for functions, to know how fast a function is growing or how fast a function is decreasing. Not just if it's increasing or decreasing, but how fast it is. And then obviously we saw some interesting points like the minimums, the maximums, that is local minimums, local maximums. We saw absolute minimums, absolute maximums. We saw x-intercepts and y-intercepts for points as well. We saw increasing and decreasing x and y-intercepts and just any points on the graph. So that ends this video on features of functions with special emphasis on the average rate of change.